Yes.
Sagar.
Sagar.
Rathod. I overpronounced the second A I learned. So it actually means ocean, right? Which I didn't. It's very there's a theme of serendipity here. Sagar got his bachelor's in environmental engineering at Gujarat Technical University in India, looking at air pollution and water treatment, and then came to University of Illinois for a master's in environmental engineering, where he was working with Tammy Bond. He then, when Tammy Bond went to Colorado State University, Sagar also went to Colorado State, also smaller boo, to get his PhD, looking at the role of iron and phosphorus in Earth's atmospheric and oceanic systems, but did some work on energy transitions and metal emissions, which we're going to hear a little bit about today. He then came to University of Wisconsin, where he worked with Morgan Edwards in the LaFollette School of Public Policy, looking at carbon removal pathways, feasibility of carbon removal pathways, and the role of ammonia in shipping. He also did some work looking at methane budgets and uncertainty in understanding methane emissions. And then I ran into Sagar upstairs in the CCR lunchroom one day, and found out that he was looking for a postdoc opportunity, and I knew that he was working with Morgan Edwards in policy, and I thought, well, there's no way that I'll, there's no way there's a match here. So I said, well, what's your background in? And he said, well, actually, it's looking at atmospheric chemistry, and that was exactly what I needed someone to come in and do some work on. So it turned out it was one of these very serendipitous moments where I realized that what he does is exactly what we needed for a project, and it worked. It's been so he's been working with Jack and I on looking at seasonality of sulfate aerosols over the northern Atlantic and North Pacific. And I can say that it's been a joy to work with him, and I'm looking forward to hearing about your work from prior to that today. So, welcome. And
thanks so much, Dan. Thanks so much for coming here, guys. As Dan said, this work is from, the metals work is from my PhD, the last paper of my PhD, and the ammonia work is something I did at the Rathod School of Public Affairs. But the general idea here is that we'll be talking about, or we'll be looking at the environmental side effects of decarbonization. So we want to move from fossil fuels to renewables as soon as possible to meet climate goals. But the pathway is not the cleanest, and it involves issues that I'll be talking about. I'll be exploring the air quality issues. There are many other issues, but I'll be looking at the air quality impacts. First and foremost, thank you so much for being here. Since we have a kind of intimate group here, we can make presentation questions. So I'm super welcome. If you have clarifying or detailed questions, they're super welcome. As I said, the purpose of this talk is to highlight two cases, the metals and ammonia, in which the air quality side effects of energy transitions could be non-trivial at global or regional level, and I'll be exploring both of those in this talk here. Now, when we say side effects, they're generally unintentional, but they could be known. Like, you take a pill and the side effects Sometimes they could be unknown, and like when we want to move from fossil fuels to renewables, the side effects, we probably know some of them, we don't know some of them. I'll be highlighting the ones that we know but are not explored in this work. The general idea again is that moving from fossil fuels to renewables on clean and green, and shipping also, currently that uses one fuel, but we also want to de-fossil fuel that sector. It creates new opportunities like jobs, it creates new opportunities like metal extractions, and just the low carbon economy creates more opportunities, but it also has some problems. And when I focus on those problems, I am playing devil's advocate here, but the advocacy is more to know those problems in detail and then see what we can do to avoid those problems in the first place. Very quickly moving, and the talk is divided in two parts, metals and ammonia. So the first few slides are metals, and then the next few slides are ammonia. But the metals part, I'm asking the simple question that, hey, we want to move from fossil fuels to renewables, and we'll need to mine and smelt a lot of metals to meet our solar, wind energy, and EV demand, electric vehicles demand. What would be the pollution, air pollution from just mining a lot and smelting a lot? Smelting is the melting of metals to purify those, and then we can use it for our purposes. What would be the air pollution from all of this in the future? And before even I describe the point, I'll give you the quick summary of the whole slide, so of the whole talk here, so that it becomes really easy to follow. Is that faster decarbonization means more purchase and installation of solar, wind, and EVs, as we all know. However, more renewable energy means more demand of metals. Like these systems are a lot metal intensive, so we will need many more like tons and gigatons of metals and minerals to meet that demand. Mining and smelting, mining is the extraction from earth or any other sources, and smelting is, as I said, is the melting of those metals to purify them. They emit air pollutants, and they create a lot of air pollution in many regions in the world, like regions such as Pittsburgh here, and other big cities like Chile in South America, and Jamshedpur in India, for example. Those are metal complexes. They have many smelting plants and so many mines around it that these processes, they contribute a lot to the pollution, local air pollution. And in the study we found that the mining and smelting, to meet this renewable energy demand in the future, it leads to more air pollution in many regions, particularly as we decrease the emissions from fossil fuel. These emissions will become prominent in some of the regions, and that is what this talk is about. That we look at how much air pollution happens in what regions, and how do they compare to the reducing, the decreasing fossil fuel emissions. And in that, now the talk starts that we have to move from carbon-heavy sources to renewable sources in the next few years, or next 20, 30 years, to meet a 1.5 or 2 degree climate goals. This is from the IRENA, the International Renewable Energy Agency's remap scenario. So what happens is energy modelers, they create pathways of how do we move from fossil fuel to renewable energy, and they use information on which of these sources is the most feasible in what region, and how they can do it, and what are the economics behind it. And they model all of these pathways to meet climate goals. And most of these modeling groups, they're finding that we need solar and wind, and they both would be the cheapest and the most feasible options in many regions. So just to meet the climate goals, we need a lot of solar and wind energy. However, a lot of these systems, they need not only the conventional metals like iron, steel, and copper, all of these systems need it, but they need some special or specialty metals as well. Like solar panels need silver a lot, and then tellurium is another one that solar panels need in detail. Wind need neodymium, which is kind of here in the rare earths metal. And EVs, as we know, like batteries need cobalt, lithium, and nickel, a lot of that. So metals do form, not only general metals, but rare earths and critical metals. They form an integrated part of our energy systems. However, these renewable energy systems, wind and solar, they need a lot more metal compared to the fossil fuel ones per nameplate capacity addition. So nameplate capacity is basically a gigaton, a gigawatt plant of solar, a solar farm, for example, a gigawatt scale or a megawatt scale of solar farm, or wind farms. They need, in general, a lot more metals than the conventional ones. So the question is that, yes, we want to move from fossil fuels to renewables. The renewables have need a lot of metals, and not only that, in terms of per unit of energy addition, they need a lot more metal.
I have a question.
Yes.
So this is just for when you're first constructing these sites, or they need constantly the metals?
That's a great question. A lot of this shows just the installation part.
Okay.
Since once you install a solar farm, you don't need more metals after that. Yes, after the life cycle, after maybe 20, 30 years, you will need to scrap it out and recycle it. But once the metal is in the system, then you don't need.
So does that per gigawatt for its whole lifetime? Is that
Yes,
what it's
that's
talking
correct.
about?
Same for these. They generally don't need new metals. Once you set up a boiler room, for example, in a coal power plant, you don't need extra metal. Then you need the rolling stock of coal or gas, but you don't need new metals.
Okay.
This just looks at the metal demand
Good.
and not the raw material. And since all of these systems need a lot of metals, this is from the IEA, the International Energy Agency, and they look at or they project the demands of some of the few critical minerals compared to what we are mining right now in 2020. And this, I think it's for a 1.5 degree Celsius goal, and they model that, say currently if you're mining at X teragrams of lithium per year, we'll need about 40x teragrams of lithium per year in 2040 compared to right now, just to meet the battery demand. Same for cobalt, which is a big part in batteries. Now this does not account, this accounts for a very slow change in the battery composition, for example, or the solar panel composition, or the wind turbines, the magnets composition. But over history or the period of the last few years, that composition has not changed. So these ones are a lot more representative of the current systems, and hopefully in the next 20 years as well. So yes, we'll need a lot more metals. And now here's where the equity and justice component comes in, that I'll also talk in this presentation, that the countries that mine the metals are different than the countries that process. The processing is basically the smelting part of it, or the refining, this is the dirtiest step in the whole process, where you actually melt the metals in furnaces and all the emissions that go out. Now that finished metal then goes to these countries for assembly to make batteries or to make solar panels and whatnot. And then there are actual countries that buy these solar panels or batteries and put them in your phones, in your cars, whatnot. And in that system, the countries, these are generally on the poorer side, these countries, whereas China currently dominates the metal smelting market. So even if cobalt is mined in Congo, it then is shipped, the raw cobalt rock is then shipped to China, where it is fused in, or it is used to make batteries, and then companies like Tesla, Apple, whatever, they use that battery to make EVs or laptop batteries or whatever, and we buy it here. So that is the supply chain here. And it causes a disproportionality, right? Like the buyers are not the manufacturers. And when we buy electric vehicles, when we install solar panels here, we have caused some emissions somewhere else that we are not aware of. And the other question here is the geographical concentration as well, that a lot of these metals are geographically concentrated. Only a small number of countries have a lot of resources and the rest don't. For example, about 60% of cobalt reserves are in Congo. Nickel, Indonesia dominates currently the nickel production, about 50 to 60% as well. Lithium, the Bolivian, Argentinian, Chilean triangle has about 70, 80% of global lithium reserves. So as we increase battery demand in all of those countries, the supply questions will start from here, and then the processing questions and whatnot will propagate through. And as I said, the mining and smelting activities already contribute a lot to particulate matter air pollution, and I'll explain what this is. The PM2.5 is the small particulate matter. In many cities, here it's only shown the example of Chile, where copper smelters, the northern part of Chile is rich in copper mines, and they also smelt it. So Chile, they don't only mine the metal, they also smelt it like there itself, and it causes about 20-30% of local air pollution in those cities, and it's true for many other cities as well. And this is happening present day. This is not accounting for if Chile mines 5x more copper in the future, then how much would this contribution be in the future? And if Chile or other countries mine more, then what would be that contribution? So this is the overarching question here again, that how much PM 2.5 air pollution from mining and smelting of metals to meet global solar, wind, and EV demand in the future. And PM 2.5 is this tiny particle of this size. This is human hair, the cross section here. And so I'm talking about really fine particulate matter, like smoke that you inhale and they go to the deeper parts of your lung. Why PM 2.5? Because mining and smelting, it emits a lot of more PM 2.5 than other gases. Greenhouse gas is a totally different question here. I'm not exploring that, but particulate matter is the one that is of more immediate human health concern than other pollutants. So what I did was use two decarbonization scenarios called business as usual and a 2 degrees Celsius goal called rapid decarbonization here, just for common words. And then in a technology-based model, we simulated what kind of smelting technologies will be in the future. They will obviously be a bit cleaner than what we have right now. What kind of abatement, so pollution control measures will be there in the future, certainly cleaner than what we have right now. And then we feed all of this demand and the technology options in a model and estimate the emissions in different regions. So the text I had in the last slide, this is the visual representation of it. We use two scenarios, one with less renewables, one with more renewables. Yes, the more renewable one will have more solar and wind and EV demand than the less renewable ones. So using this, we grab the EV, solar, and wind energy projection demand. Now, all of these demands, it triggers a metal requirement, in the units of, if you add 1 gigawatt of solar panel in region X, it triggers a Y gigawatt of metal demand, and all metal demand in different regions, proportional to where mining happens right now. This metal demand is met via various processes, such as mining and smelting. And then these processes emit health and climate-relevant air pollutions, but currently I'm focusing on just particulate matter here. So going on to the results, I have a few slides here, but the general idea here is that the x-axis shows time, the y-axis shows the gigagrams of PM 2.5 emitted from mining and smelting just to meet the metal demands. And now these numbers are abstract. I put them in the context in the next slide. But the general idea, and these colors are different macro regions. Some of them are just individual countries like India and China, and Russia, but others are just macro regions here. The general idea is that and this is the current energy policy, is a slower decarbonization scenario. This is a faster decarbonization scenario. That yes, if we add lesser renewables, we'll have lower emissions. If we add more renewables, we'll have higher emissions. The countries that will bear the burdens are different. India, because it will do a lot of more smelting, it is adding a lot of more metal processing and smelting capacities, might be a hotspot of metal emissions in general. But there are other countries such as China and Europe that, because they have a lot of, Eastern Europe particularly, that has a lot of more smelting capability right now, they will also experience a lot more emissions in the future. Now this dotted black line is the stringent mitigation. It is a case where we keep the metal demand same, but just vary the abatement strictness. So you can have the same smelting power plant using the same smelter, but the end of pipe controls are stricter in this line. And we find that, yes, if we trigger those in different countries based on observed penetration of abatement in different regions, we find that, yes, they decrease very quickly, and that stringent, stronger abatement is actually can reduce about 90–95% of total emissions. As I said here, that stringent abatement, even in a case with high renewables, can reduce a lot of emissions. So,
Sagar, can I ask a quick question? So does that technology exist right now with like scrubbers and filters and things to do that black line, or is that reliant on technology that does not exist yet?
We use the current available technologies. Okay. The question is, in stringent mitigation, say a country like India where you have n number of smelting power plants, only a few of them have those scrubbers installed. In the stringent mitigation, we assume that more smelting plants will have those scrubbers installed. And now this is where I put the numbers to context where what those numbers meant. Here, the black color here is the anthropogenic combustion emissions of all the coal power plants, gas, other power plants, or all the energy sources that we burn emit smoke as well, or PM 2.5. So those are these big values here. Compared to those, the mining and smelting ones are tiny. Yes. The red dashed line shows the ratio of orange divided by orange plus black. So it's like mining divided by total. And it's in a scenario where we transition slowly, it's about only 3% of global, where we see that, yes, the overall anthropogenic emissions will go down as we transition. And the mining ones might go up. The orange increases very slowly, that this is not a big value. However, in a scenario in which we move very fast to renewable energy to meet a 2-degree climate goal, our emissions will decrease very rapidly, basically getting half. And the mining and metal-related emissions may reach around 8 to 9% in the future. Now this 8 to 9% is a global value, and then the next slide I'll show how they vary regionally. But the general idea of this slide is that faster decarbonization wins. Like even if we have this orange line that no one considered before and we consider it, even if you add it here, the sum of this is not as big as the sum of this. So even if you do faster decarbonization and we have to account for the mining and smelting emissions, the sum is smaller than the total sum. Yeah. Yes?
I have a quick question, a clarity question. So I'm assuming that between these two scenarios, there's a tug of war going on, so that in the slower one, as you slowly decrease something's mitigating that certain jump, which is happening in the rapid one, when you suddenly decrease. Like when you suddenly go rapid decarbonization, that increase is coming from some technology or something which is not able to keeping up with that steep change. Do you know what that change is, which is like causing that jump, or am I understanding it?
Yeah, no, that's a great question. Yes, if we decarbonize very quickly now, and if we need a lot of metals right now, countries are not equipped with proper scrubbers, like as of today, and that our technologies are not the most emission efficient technologies. So the timings aspect is important here, that when do we decarbonize, when do we mine and smelt more, when countries are prepared to take that hit, or right now when a lot of countries are not even equipped with that capability. So, and this is, the previous slide was global, where it reaches around 8 to 9% in the rapid decarbonization scenario, but the general idea here is that emission burden is not equally distributed. And here I segregate the global with India, China, India, North America, and EU, and the rest of the world. And I'll just focus on India and North America as a contrast between a middle income and a high income country or region. And regardless of the emission energy pathway of less or more renewables, countries which do not participate a lot in mining and smelting right now, such as the North America and EU regions, there the percentage of mining to total will be very small, almost a 1 to 2% at max. Whereas countries that are currently participating, India and China, there the contribution of mining could be as high as 15 to 16%. So yes, while the whole world moves from renewables to fossil to renewables, some countries will get that hit, whereas others might not get that. So that causes equity and justice question as well, where we want batteries, we want EVs, we want solar panels, but who is going to do the mining and smelting for it? And what will be the implications for those countries? And even in India, like it's in China, it's not the country in general, it's only a few mining towns that will bear a lot of this burden. So yes, on a country average, it comes out to about 16%, which is a high number, but on a regional basis or sub-regional basis, it could be an even higher number. Yes.
So what are the barriers to adopting more scrubbing technology? Is it just financial, or is there like, does it change the efficiency of energy production? What is the...
Currently, it's financial, I would say, and there's not a lot of political incentive either. in low-income or middle-income countries, air pollution is often not in the top 10 agenda items for policymakers to run for office, for example, or people to vote for. It is getting some traction now, but only in hotspot cities, but not elsewhere. And often mining and smelting happens in relatively like moderately populated town in India and China, so there it's often goes out of attention. So it's both, I would say, it's financial, it's to cut costs wherever these companies can, and the lack of political is what.
How much of a, well, like what percentage of an operating budget would, are you looking at costs for this?
I don't know, but it would be a smaller budget, I would assume. Given these companies own big mines and have big smelting plants, the control would be a relatively smaller budget. However, it's still a cost, and these companies try to cut the cost. So the last two slides on the metal question is that we looked at these discrepancies between different regions getting different amounts of the pollution burden, but how do we estimate that, or how do we quantify that? And we use principles from economic theory or income inequality economics, where we generally know this graph where a small amount, or the first 60% of the people, they earn only 40%, and the last 10% of the people, they earn 30% or higher in different contexts. And this is called the Gini index, the Gini way of representing it, where the area under the curve, if it's smaller, it's more equal society. If it's bigger, then it's an unequal society. Now for the metal case, we looked at the snapshot of 2040 for all metals. So it's not only looking at steel or aluminum or any particular metal, but just all metals. And we looked at, and we find that with a slower renewable energy addition with BAU, so moderate abatement, about the countries that demand about 60% of metal, they themselves are emitting about just 20%. So think of North America and EU that are adding a lot more EVs and batteries right now, and that represent about 50% of the global EV additions. They themselves are emitting about 20% of emissions. But the other countries that represent only 40% of the demand, they are bearing a lot of this burden. However, if we increase abatement alone, not changing where mining happens, where smelting happens, if we just increase abatement alone, we can reduce this inequality. The inequality reduces in the model where now the countries that demand 60% of emissions, they represent higher emissions, and the goal is to not make it equal, and the overall emissions are also lower in the stringent abatement. But on top of that, they are more proportionally divided. It's not, the disproportionality is lower as well. What does it mean for us, for the US? Is that the current government and the previous government as well, they're very much pro self-critical mineral reliance. That is, we don't want to depend on other countries for our critical mineral needs. So the current government has incentivized a lot of local exploration, lots of local lithium and nickel and cobalt mines are being explored, and they're fast tracking a lot of the opening and commissioning. The next one is a relatively shorter topic about ammonia for shipping. Here the summary is that the shipping sector uses a lot of diesel and heavy fuel oil right now, and it emits about 2% of global carbon dioxide, anthropogenic carbon dioxide. On top of greenhouse gases, it also emits smoke, and the smoke causes about 80,000 or more premature mortalities due to air pollution alone, dominated near port areas. So modeling groups, so the energy models, again, they predict ammonia is the future shipping fuel. So if you want to move from fossil fuel to renewables in the shipping sector, which is very hard to decarbonize, by the way, they think ammonia, which burns cleanly, which does not emit smoke, on carbon dioxide, it does not emit either, could be a good shipping fuel because you don't have to change the engine type a lot. However, the ammonia emissions, they have come with their own problem, and one of the problems that I'm looking at is that while in the air, they form secondary particulate matter. Now, secondary particulate matter is, the ammonia is emitted as gas, but it fuses with more ammonia or it fuses with some other particles or gases to make secondary particles. So it was emitted as gas, but then it became smoke, or then it became particle while in the air. So it reacts with sulfates and nitrates in the air to make particulate matter. Now the context or the specific example I'm looking at here is the port of Singapore, which sells about 20% of global shipping fuel right now. And we looked at the case that what if Singapore, instead of selling a lot of diesel, if it sells a lot of ammonia, then what would happen because of leaks and what would happen to air quality and public health due to the ammonia leaks, or possible ammonia leaks. And we found that these emissions could be about 70% higher than the baseline, so a lot higher, and they can lead to about a similar, a factor of 3 higher than the emissions in the premature mortality in the future year 2050. So this is only a 2050 snapshot where we look at what would happen if Singapore, instead of selling diesel, sells ammonia in 2050. As I said, all the shipping impacts are located near ports, so all the port areas in India, Europe, and all the port areas of China, they have a lot of shipping burden, including in the US, where the LA and the New York ports, including the port Savannah, I think in Florida, that has a lot of air pollution impacts as well. The ship fueling operations is the question here, that they are really concentrated. Singapore sells about 20%, about more than 20% of the global heavy fuel oil or diesel to all the ships. So imagine a ship that started its journey from, say, Japan, but it was delivering something in Dubai here. It would go through all of this. It would make a stop in Beijing, may not, Beijing, somewhere near Shanghai or somewhere. Then it will go through here. It will stop at Singapore because it will get cheaper diesel to refuel. Then it may make a stop in Sri Lanka, Mumbai, and then go to Dubai. Or may even go to somewhere in Europe via the Suez Canal. So the gist is that a lot of ships stop here for the fueling or refueling operations. The US Gulf is a big port as well, and so is New York and Ellicott Beach. To put things into context, imagine this quick trip on University. It's selling about 20% or more of the total gasoline that was sold in all of Madison and Sun Prairie, Fitchburg, Illinois, and maybe add a few more towns here and there. And it would still sell 20% more. Imagine the lines that you'd have at this quick trip just to meet, because it's a big gas station. Now, how does ammonia come in the picture? Very similar story as the metals one, so I'll rush a bit more here, but the idea is that currently, yes, we use ammonia, about 200 million tons, and this existing uses is all for fertilizers. It basically is 90-95% of produced ammonia for fertilizers. The rest is for different products such as fuels. But in the future, and this is again an IEA, so International Energy Agency modeling prediction or projection, and then they think that in the future for the net zero energy scenario, we'll basically double the ammonia demand. So if you're making around 200 million tons just for fertilizers, we'll need to add about 200 million tons of ammonia just to meet the maritime fuel or the shipping fuel demand, if we want to move from ammonia, heavy fuel oil to shipping. The catch here is that ammonia is leaky. It contributes to secondary aerosol formation or secondary particulate matter formation, and it is difficult to abate. The difficult to abate part is, right now it's not explored at all because no one knows how to do ammonia storage and shipping at ports. We know how to do it in more organized way in industries, but doing at a port where you have ships coming in and out, all of these is in the unknown territory, but these are slightly more known here. So here I'm asking the same question as I did for the metals question, that what could be the ammonia emissions from storing and bunkering it in ports, and what could be its implication for air pollution. Storing and bunkering, the word bunkering basically means fueling in shipping terms. So I looked at, if we store a lot of ammonia here, what could be the emissions here because of the leaks? And also while we fuel using pipes and valves, and those valves can be leaky, what could be the ammonia emissions from here, and when they are in the air, how they can fuse with different pollutants to make particulate matter, and when we inhale them, what could be the public health effects due to that, but only at the port of Singapore here, because the idea is that Singapore is currently selling a lot of diesel, but if it wants to maintain its dominance as a shipping or fueling hub, it will transition to ammonia at some point. It's currently giving rebates and tax benefits to ships that come with an ammonia using engine, and they have some sort of ship-to-ship operations going on right now. They don't have port storage right now, but they are thinking about that. Again, simple methodology is that we used energy equivalency to estimate ammonia quantity. So if Singapore is selling 100 tons of diesel right now, 100 tons of diesel has 100 multiplied by water joules per kilogram of energy. We multiply that with ammonia's joule per kilogram of energy to estimate ammonia quantity required. Now leak values are from current literature, so they are not the most representative because we don't know how much abatement can be possible or how much leaks might happen. But the general idea from a few studies is that it's 0.05% of stored ammonia that might leak out. And ammonia emissions are then simpler to calculate, is that whatever ammonia we are storing multiplied by some leak factor. Then we plug these ammonia emissions into a reduced complexity equality model. This was done in collaboration with the Austrian group YASA. And then we use some concentration response curves to estimate the health impacts of those ammonia emissions, or the particulate matter emissions. A few results here. This is the baseline 2050. So imagine a 2050 Singapore and look at the ammonia emissions. And 2050 Singapore, a lot of the ammonia emissions will come basically from agriculture, whatever stock they have, livestock they have, and some agriculture that they have very little, but whatever that is. And we considered some medium leak and high leak scenario, just teasing with the tweaking the leak factor. And we find that even with the conservative leak factor, this ammonia emissions just from these two sources can more than double the ammonia emissions at Singapore. And if you use a higher leak factor, we use a factor of 3 compared to the base one, it could be much more. And then we plug these values in a model and to see what could be the impacts on PM 2.5. The general idea is that, yes, if we have more ammonia, we'll have more air pollution. However, in the high leak, the air pollution can be about 50% higher than our baseline. And the red one here is the one the red one here is the contribution from heavy fuel oil in 2050. So we also simulated a case in which we assumed that, okay, in 2050, Singapore might still use heavy fuel oil. So this is our control case. In the emissions case, we replace this red and plug in the ammonia emissions, and we find that if we have ammonia emissions, then the resulting particulate matter could be higher than what we can have with using heavy fuel oil. And same with the high leak, that if we plug in slightly higher numbers, we get more particulate matter concentrations. Again, these numbers are abstract. How do we put them into context? Is by doing some premature mortality calculations or health impacts. Is that currently this is our 2050 Singapore snapshot. So in 2050, the heavy fuel oil emissions may contribute to about say 650 to 750 is about 100 deaths. But the ammonia emissions may contribute to a lot more deaths due to that. Now this deaths is an estimation based on how people respond to changing air pollution. That is, at every increase of a few micrograms per meter cube, we look at hospital records and see, okay, the pollution increased by a few micrograms per meter cube, our health damages, people admitting to hospitals and some of them dying due to that increased by a few percentage. And those health response curves are developed over years and years of hospital data and air quality data as well. But the general idea here is that if we move from heavy fuel oil to ammonia, yes, at ports, it can increase the health burden. However, of the total fuel that is sold at Singapore, about 20% of it, it causes 16,000 deaths right now, everywhere. So we are replacing the 16,000 deaths with 600 deaths. But these 16,000 deaths happen, it happens, I will not say proportionally, but it happens everywhere. However, these 600 happen at Singapore itself. So it again raises this question of equity and justice, where we are replacing a lot more deaths, more equally spread to something that is more regionally concentrated. And this is something, a very recent development that the Singapore's Global Center for Maritime Decarbonization, they recently commissioned a study to see ammonia bunkering and safety, and it's done with industrial partners to see if it's safe. However, they are not, in this study, they are not looking at air pollution impacts of ammonia. The context for US is fairly simple. We have the third and probably the seventh and ninth largest ports in terms of fueling and refueling of ships. So we do sell a lot of diesel. And the US Department of Homeland Security and the Congress are looking at ways to, first of all, safeguard a lot of these ammonia storage. Because if you have ammonia, a lot of ammonia sitting at your ports, they can be easy targets as well. They can also have just ammonia being a very combustible gas. They can have other safety aspects. So the government is looking at, and this is all very new development as well, that the government is looking at all of the ammonia question using a safety angle, but they are not considering a quality angle yet. Hopefully they will consider it in the future. But in summary, the whole slide could be an email in that the regional impacts could be non-trivial in a global energy transition. Yes, we want to move from fossil to renewables, but someone, like a small group of people, or the impacts could be very regionally concentrated, and we need to consider them. So with that, I'll put these figures back on it. Thank you.
Great, thanks very much, Sagar. We have some time for questions. I'll let you call on people.
Yeah.
How do you produce enough ammonia for replacement of that? Like, I don't know much about ammonia, and like, is there a risk of ammonia production plants, and like, do they emit a lot of gases and other things as well?
Yeah, that's a great question. A couple of things. Singapore itself does not make a lot of diesel. It imports a lot of diesel and then it sells. So Singapore is a selling hub, a trading hub. We think it could be the same for ammonia, where it will import a lot of ammonia from elsewhere, like China or India, and then it will basically be a shipping hub to just sell ammonia. Regarding production of ammonia causing a lot of emissions, the global shipping, diesel combustion and shipping causes about 2%, 3% of emissions. The global ammonia production currently causes about 2 to 3% emissions. So what the modeling groups are thinking is to make ammonia more green by doing water's photolysis, or any lysis, electrolysis, to get that hydrogen needed to fuse with nitrogen. So they're trying to make green ammonia in the future. But then doing more green ammonia needs more renewable energy, and that feeds into the other question.
I have two questions. One, I'm just curious how it's calculated, like what these deaths are coming from. Like, how is it quantified that the deaths are from shipping specifically?
Oh, that's a great question. We do a with and without simulation.
Oh, okay.
We run the model, the concentration response model, with all emissions on and with just the baseline emissions on. And the difference is what we show here as the blue color here.
Okay, and then my other question was, is there like a pathway where maybe Singapore doesn't have so much of the like fuel coming from the air, like where other countries are doing that as well?
That is a great question. I see that. Would Singapore want to leave that power position? Is the question. And to maintain the dominance it is currently giving, and many of the ports are giving a lot of rebates and tax benefits to ships coming there and getting fuel from there. So, but in that, you raise a great question that energy transition also provides opportunity to decentralize more things, that yes, more countries can now participate if they just sell ammonia or sell shipping friendly fuels. However, I don't know if there will be other ports that will take that position. It's also very strategically located between Asia and Eastern Africa, or the gateway to Europe. So I don't know how that can pan out in the future.
A couple of questions about ammonia as a fuel. So byproducts of that, I presume, are like nitrogen and water, is that? Or what's the?
Yes, when you burn ammonia.
Yeah.
If you completely burn or 100% combustion, then it should lead to nitrogen and water. Incomplete combustion can lead to N2O, which is a greenhouse gas.
Yeah.
So the second or third largest greenhouse gas.
And a particularly effective types of one. Then I guess the other question, efficiency of the energy getting out of burning ammonia versus burning fossil fuels. Is there similar efficiency in terms of the amount of energy per, I guess, greenhouse gas per unit energy produced?
If you're looking at the life cycle of how ammonia is produced currently, it is greenhouse-wise, it's the dirtiest fuel, one of the dirtiest fuel, because of the, and a lot of emissions happen while producing ammonia itself, not even storing and whatnot.
With greenhouse gas?
Yes, with
Yeah.
greenhouse
Or with the fossil fuels?
Yes, compared to that. Because current ammonia manufacturing needs a methane steam reforming to just tease out that hydrogen that we then fuse it with nitrogen. So even the current ammonia production is dirty with respect to greenhouse. However, the engine combustion efficiency, the thermal efficiency of an engine, some companies have gotten to similar levels as heavy fuel oil or diesel engines. So it's on the combustion side, it's the efficiency is similar, but on the production side, ammonia is slightly dirty, or more dirty than diesel right now.
How do you ask?
Oh, I mean, there are efforts at like trying to, if you can produce ammonium from renewables, which I presume is the assumption here, and then also there are efforts at actually using ammonium as a battery, as a fuel for batteries rather than necessarily just combustion, which changes the efficiency of how you get power out of that. But that's all. Who knows what's going to happen with that actually evolve.
Yes, so one of the pathways is also converting ammonia to hydrogen in some fuel cell, or a converter just before you burn hydrogen. Hydrogen burns slightly more cleaner, slightly more efficient than ammonia. So you store ammonia in your ships, and then just before combustion you convert it to hydrogen and then burn hydrogen. So it reduces some of those N2O questions on the aspect.
I guess I had a question to you and everyone in the room if someone knows this, but your first talk, it seems to be there's two possible scenarios based on the data available that this is how it could look. Using the same thing, is there a way to fit a model which could be like a best case scenario, like how much carbonization or decarbonization should happen so that it's most equitable? I know like we are limited by the simulations, but using the data, could there be a simpler model to come up with a situation like this gradient or this changes would be more equitable, I guess?
Yeah, that's a great question. And the timing aspect is more important here. Like, when do we decarbonize? Like, do we decarbonize after we have all the instruments and proper technologies versus not? And while we can solve for optimizing that, I think for greater global interest, it is important that we reduce everything as soon as possible. Yes, this increases disproportionate burden to some countries, but instead of waiting for those countries to install, say, proper scrubbers or electrostatic precipitators, there could be a policy solution where which countries can pay those mining and smelting countries to install those scrubbers. So instead of waiting for that and optimizing the model for that, there could be a policy aspect where rich countries incentivize low-income countries to mine more sustainably.
For shared technologies, like
Yeah.
different pathways. Okay, that makes sense.
Yeah. mean, this isn't a technological issue, this is a financial issue at this point, right? Because we have the technology
Yeah.
to reduce that curve.
Yeah.
It's political.
Yeah.
Just on a single project level, do you think there's potential to integrate some of these externalities, like equity-based externalities, into cost-benefit analysis that goes into making these policy decisions on a project level?
Air pollution is generally difficult to quantify. A lot of cost-benefit calculations already include carbon dioxide, which is your largest externality, or carbon dioxide and methane and other things. But air pollution generally is not part of those impacts, since it's difficult to calculate the health impacts and tell the value of statistical life and a lot of that at different regions. Like for the US, we do know we do have a better idea of the value of statistical life, but for other regions we don't, and that makes it the cost benefit difficult for these models.
Any questions? All right, well, let's thank Sagar again for his great talk.